Every detail in this story comes from real scientific research and observation. There is something holding the universe together that no one has ever seen. Not a force anyone has touched, not a particle anyone has caught, not a wave anyone has measured directly. Something that passes through your body right now, billions of particles per second, without leaving a single trace, without slowing down, without interacting with a single atom inside you. It has been doing this for 13 billion years. In 1933, a Swiss astronomer looked at a cluster of galaxies and wrote down a number that didn't make sense. The galaxies were moving too fast, far too fast. They should have flown apart billions of years ago. Something was holding them together, something he could not see. He called it Dunkel Materia. Dark matter? No one listened for 40 years. Then a woman named Vera Rubin sat down with a telescope and a roll of photographic film and started measuring how galaxies spin. And what she found broke the rules. The outer edges of galaxies were moving at the same speed as the centers. That is not what gravity allows. Not if the only mass present is the mass you can see. Something else was there. Something vast. Something invisible. Something wrapped around every galaxy in the universe, like a shell that cannot be photographed, cannot be weighed, cannot be touched, but without which none of this exists. No galaxies, no stars, no planets, no you. Tonight, you are going to follow that discovery from the beginning. You are going to stand at the moment it was first suspected, trace it through decades of resistance, and arrive at the present day, where some of the most sensitive instruments ever built sit in mines 1.5 miles underground, waiting in silence for a signal that has not yet come. The universe is mostly made of something no one understands, and the search for it is one of the strangest, most patient scientific investigations in human history. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. For most of human history, the night sky was everything. It was the clock, the compass, the calendar, and the mystery. People watched it for patterns. They recorded the motion of planets across constellations. They measured the distance to the moon by parallax. They calculated the mass of the sun by the way Earth orbits it. Piece by piece, century by century, astronomers built a picture of the universe that rested on one foundational assumption: what you can see is what is there. That assumption was wrong. The universe you can see, the stars, the gas clouds, the planets, the dust, the light itself, makes up approximately 5% of everything that exists. 5%. The remaining 95% is divided between two things that have no satisfying explanation. 27% is dark matter, 68% is dark energy. Together they are the dominant ingredients of the cosmos. Together they are almost entirely unknown. Tonight, you are going to move through the story of dark matter, not as a list of facts, but as a sequence of moments. The observations, the calculations, the arguments, the resistance, and the gradual reluctant acceptance that the universe is not what it looks like. You are watching this unfold from a vantage point outside time, outside place. You can see the telescopes and the data and the long nights and the slow turning of scientific consensus. You are the observer, and what you are about to observe took almost a century to come into focus. We begin in 1933 in Pasadena, California, at the California Institute of Technology. Fritz Zwicky is a difficult man to like. He is brilliant and combative and dismissive of colleagues he considers beneath him, which is most of them. He is Swiss-born, volcano-tempered, and possessed of a scientific imagination that frequently outruns the evidence available to him. He has already proposed correctly that supernovae are a distinct class of stellar explosion, far more energetic than ordinary novae. He will later predict the existence of neutron stars before anyone has any idea how to detect them. He is, in many ways, ahead of his time in ways that frustrate him deeply. In 1933, Zwicky turns his attention to the Coma Cluster. The Coma Cluster is a collection of galaxies approximately 320 million light-years from Earth, in the direction of the constellation Coma Berenices. It contains over 1,000 galaxies. It is one of the densest known concentrations of galaxies in the observable universe, and Zwicky wants to know how much it weighs. He approaches this in two ways. First, he estimates the mass of the cluster by counting the galaxies and estimating how much a typical galaxy weighs, based on the luminosity of its stars and the known relationship between stellar brightness and stellar mass. This gives him a number, a luminous mass, the mass of everything he can see. Then he measures how fast the galaxies in the cluster are moving relative to one another. This is done through the Doppler shift, the way light from an object moving toward you is compressed to shorter, bluer wavelengths, and light from an object moving away from you is stretched to longer, redder wavelengths. By analyzing the spectra of the galaxies, Zwicky can calculate their velocities. The velocities are far too high. For the Coma Cluster to hold together, for gravity to prevent the galaxies from simply flying apart at those speeds, the total mass of the cluster would need to be approximately 400 times greater than what the luminous matter alone could account for. The stars and gas that Zwicky can observe make up less than 1% of the mass required. He writes a paper, he publishes it in the journal Helvetica Physica Acta. He states plainly that there must be large amounts of what he calls, in German, dunkle Materie, dark matter, present in the Coma Cluster, matter that does not emit light, matter that cannot be observed directly, matter whose existence is inferred only from its gravitational effect on the things around it. The paper is noted, and then largely ignored. This is not unusual in the history of science. A single anomalous measurement from a single cluster of galaxies, reported by a man with a reputation for making dramatic claims, it doesn't carry the weight needed to overturn a foundational assumption. The assumption is that the universe is made of the matter we can see. The burden of proof is high. One data set from one difficult astronomer in 1933 is not enough. So the question is set aside. The decades move, the telescopes improve, the physics of stars and galaxies becomes more sophisticated, and the anomaly that Zwicky found waits, patient and unresolved, in the scientific literature. You are watching this from outside. You can see the paper sitting in archives, referenced occasionally, quietly accumulating dust. You can see the data, the velocities, the mass calculations, the discrepancy that is too large to be a measurement error, waiting for someone to look at it again with enough tools to take it seriously. That moment will come, but not yet. In the years after Zwicky's paper, astronomers continue building their understanding of the universe on the foundation that light is the primary tracer of mass. If you want to know how much matter is somewhere, you measure how much light is coming from there. The more luminous a region, the more stars it contains, and stars are made of matter, so luminosity maps mass. This is a reasonable assumption. For a long time, it works well enough. The orbits of planets in our own solar system follow Newtonian gravity with extraordinary precision. The moon's orbit around Earth is predicted to extraordinary accuracy. Mercury's slight orbital precession is explained perfectly by Einstein's general relativity. The framework is robust. The framework has earned its trust. But galaxies are not solar systems. In a solar system, nearly all the mass is concentrated at the center, in the star. The planets are negligible in mass by comparison, so the further a planet is from the star, the more slowly it orbits, because the gravitational pull weakens with distance. Mercury orbits the Sun at 47 kilometers per second. Earth orbits at 30. Neptune, far out at the edge of the solar system, crawls along at just 5.4 kilometers per second. This is what Kepler described in the early 17th century. This is what Newton explained mathematically a few decades later. It is one of the most tested relationships in all of science. If the same principle applies to galaxies, and there is no obvious reason it shouldn't, then the outer regions of a galaxy should orbit its center more slowly than the inner regions. The bulk of a galaxy's mass is concentrated at its center, in the dense core of stars and gas. The outer arms should thin out and slow down, just as Neptune slows relative to Mercury. In the 1960s, this is what almost everyone expects to find when they look carefully at how galaxies rotate. They are wrong. The first serious crack in that expectation comes from work by Vera Rubin, an astronomer at the Carnegie Institution of Washington, and her collaborator Kent Ford, who has designed and built an exceptionally sensitive spectrograph, a device for splitting light into its component wavelengths and measuring the Doppler shifts of individual regions of a galaxy. Rubin and Ford begin with the Andromeda Galaxy, the large spiral galaxy approximately 2.537 million light-years from Earth, the nearest large galaxy to our own Milky Way, visible to the naked eye from dark locations in the northern hemisphere as a faint smudge of light in the constellation Andromeda. They want to measure the rotation curve of Andromeda. A rotation curve is a plot of orbital velocity against distance from the center. For a galaxy dominated by a central mass concentration, this curve should rise steeply near the center, peak at some intermediate radius, and then fall steadily as distance increases, the classic Keplerian decline. What they find instead is a curve that rises and then flattens. The outer regions of Andromeda are not slowing down. They are moving at nearly the same velocity as the inner regions, in some areas at essentially the same speed across a vast range of distances from the center. The rotation curve is flat where it should be declining. This is published in 1970, and like Zwicky's paper 37 years earlier, it is received with a certain amount of skepticism. Perhaps it is a peculiarity of Andromeda. Perhaps there are measurement uncertainties. Perhaps the spectrograph, however sophisticated, is introducing errors. Rubin and Ford do not stop with Andromeda. They extend their survey to other galaxies. They study spiral galaxies of different sizes, different orientations, different distances from Earth. They measure rotation curves for galaxy after galaxy. The result is always the same. Flat rotation curves everywhere, consistently, across dozens of galaxies, spanning a wide range of types and sizes and distances. The outer regions are moving too fast. By the mid-1970s, Rubin has measured the rotation curves of more than 60 spiral galaxies. Every single one shows the same pattern. This is no longer a single anomalous measurement. This is a systematic result. This is what the data looks like across the universe, not just in one unusual place. And now the question becomes unavoidable. Why? There are two possible answers. Either the law of gravity is wrong. It does not behave the way Newton and Einstein described at galactic scales, or there is matter in these galaxies that is not visible. Matter distributed not just in the luminous disk that we can see, but in a vast extended halo surrounding the disk. A halo of matter that contributes gravitational mass without emitting any detectable light. For the rotation curve to be flat at large radii, the mass enclosed within any given radius must continue increasing as the radius grows, even as the luminous matter thins out and fades. The only way that works is if there is invisible matter extending well beyond the visible edge of the galaxy, distributed in a roughly spherical halo with a density that falls off slowly with distance. This is the dark matter halo hypothesis. It is not a comfortable hypothesis. It requires accepting that the visible universe, everything astronomers have been studying for centuries, is embedded in and outweighed by something they cannot see at all. But the data is the data. You are watching Vera Rubin present these results at scientific conferences. You can see the audiences, the skepticism, the questions, the alternative explanations being proposed, the reluctance to accept and answer this radical. Dark matter is not a welcoming concept. It asks for a fundamental revision of the cosmic inventory. It demands that the map of the universe be largely redrawn. And yet the rotation curves do not change. The data does not bend to the discomfort of the people looking at it. By the end of the 1970s, the scientific community is beginning to shift. Not all at once, not without resistance, but the weight of evidence from galaxy after galaxy, rotation curve after rotation curve, is accumulating to a point where the alternatives are becoming increasingly difficult to defend. The simplest explanation, and in science, the simplest explanation that accounts for all the data, is usually the right place to start, is that there is matter out there that we cannot see. How much matter? The luminous matter in a typical spiral galaxy, the stars, the gas, the dust, everything that emits or absorbs light, accounts for only a fraction of the mass required to explain the rotation curves. The dark matter halo surrounding it must be several times more massive than the visible galaxy it encloses. In many cases, the ratio is 5 or 6 to 1, in some cases higher. The galaxy you can see is just the bright core of something much larger and much heavier. You hold that thought. You let it settle. The Milky Way, our galaxy, the one you live inside, the faint band of light that crosses the sky on a clear dark night, is itself embedded in a dark matter halo. That halo extends to a radius of approximately 200,000 light-years or more from the galactic center, far beyond the visible disk of stars that spans roughly 100,000 light-years. The total mass of the Milky Way, including its dark matter halo, is estimated at somewhere between 700 billion and 2 trillion times the mass of the Sun. The stars alone account for only a fraction of that. You are inside a dark matter halo right now. You have been your entire life. Every cell of you, every breath, every moment of consciousness, all of it has taken place inside this invisible structure that you cannot sense, cannot touch, cannot detect with any of your biological equipment. It passes through you. through the walls, through the floor, through the planet below you. Billions of particles, if they are particles, streaming through every cubic centimeter of space at hundreds of kilometers per second, not stopping, not interacting, not leaving any mark on any atom in their path. This is where the science stands as the 1970s give way to the 1980s. The evidence for dark matter is strong. The rotation curves are consistent and reproducible. The mass discrepancy is too large and too systematic to be a measurement error or an observational bias. Something is there. But what is it? That question, the most important question in modern astrophysics, and arguably in all of physics, is still open, still unanswered, still driving some of the most ambitious and expensive scientific experiments on the planet, right now, tonight, as you listen to this. The search for the identity of dark matter is the story of the next several hours. But first, there is one more thing to understand about what Rubin and Ford found, and why it matters beyond the rotation curves alone. When you measure a galaxy's rotation curve, you are not just measuring velocities, you are measuring the distribution of mass throughout the galaxy. You are mapping indirectly the shape and extent of whatever is producing the gravity that governs the motion of every star you can see. And what those maps reveal is not a thin disk of invisible matter mirroring the visible disk. What they reveal is a halo, roughly spherical, extending far beyond the visible edge of the galaxy in every direction, concentrated toward the center but present throughout, with a density profile that falls off gradually with distance. This three-dimensional structure, the dark matter halo, is not just an abstract concept, it is a real physical structure. It is the scaffolding inside which every visible galaxy lives. It was there before the stars formed. It shaped the process by which gas collapsed and stars ignited. The visible galaxy formed inside the dark matter halo, not the other way around. You are watching the Milky Way from outside now, from a distance of, say, 1,000,000 light years. From here, you can see the luminous disk, the flat spiral of stars and gas clouds, wound into arms that trace bright arcs across the center. It is beautiful. It is unmistakably there. But surrounding it, invisible to any optical instrument, is the halo. It is 5 times larger. It is 5 times heavier. It predates the stars inside it, and it is made of something that physics in 1980 cannot identify, cannot produce in a laboratory, and cannot detect directly with any instrument that exists. The year is changing. The decade is turning. The evidence has spoken. Now the question is, what is it? That question will carry us forward through the night. The rotation curves were the first clear, systematic evidence, but they were not the only evidence. As the 1980s progress, observations from completely different directions, different instruments, different wavelengths, different physical phenomena begin to converge on the same conclusion. The universe contains far more mass than can be accounted for by ordinary matter. One of those independent lines of evidence comes from something called gravitational lensing. Albert Einstein predicted in his General Theory of Relativity, published in 1915, that mass curves space-time. This is the core idea of general relativity. Matter does not exert a force across empty space, as Newton imagined, but rather matter warps the fabric of space-time itself, and other matter moves along the curves produced by that warping. The more mass concentrated in a region, the more severely space-time is curved around it. One consequence of this is that light, which travels in straight lines through flat space-time, follows curved paths through curved spacetime. Near a massive object, a beam of light is deflected. It bends around the mass. This effect was first confirmed during the solar eclipse of May 29, 1919, when Arthur Eddington observed stars near the limb of the sun and found that their apparent positions were slightly displaced from where they should have been. The light from those stars had been bent by the sun's gravity as it passed close to the solar surface. Gravitational lensing scales with mass. A galaxy cluster, far more massive than a single star, can bend light dramatically. It can take the light from a distant galaxy behind it and distort it into arcs, or rings, or multiple images, depending on the alignment. And by measuring how severely the light is bent, by measuring the distortion, you can calculate how much mass the lensing object must contain. In the 1980s and 1990s, as gravitational lensing becomes a practical observational tool, astronomers begin applying it to galaxy clusters, and the results are consistent with everything the rotation curves had suggested. The total mass required to produce the observed lensing is far greater than the mass of the visible matter alone. The discrepancy is the same order of magnitude, roughly 5-to-1 matter to visible matter across cluster after cluster. This is important because gravitational lensing is a completely independent measurement technique. It does not rely on Doppler shifts. It does not rely on spectroscopy or assumed mass-to-light ratios. It relies on the geometry of spacetime and the path of light, and it arrives at the same answer. Something unseen is producing gravity, a lot of it, everywhere astronomers look. You are settling now. The history is moving through you. The telescopes, the spectra, the calculations, the converging lines of evidence from different methods across different decades, each one pointing in the same direction, each one adding its weight to a conclusion that is becoming harder and harder to avoid. The universe is not what it looks like. The matter you can see, the matter you are made of, the matter that makes up everything you have ever touched or tasted or breathed, is a minority constituent of the cosmos. It is the 5% that glows, surrounding it, threading through it, holding it together and shaping its structure, is something that does not glow, does not interact with light in any way that has yet been detected, and whose fundamental nature remains, at this moment, one of the deepest unsolved problems in science. Because knowing that dark matter exists, or rather that something producing its gravitational effects exists, is only the beginning of the question. The harder question is what it actually is. And to approach that, you have to understand not just galaxies and galaxy clusters, but the universe as a whole, its history, its structure, the way it evolved from a hot, dense beginning 13.8 billion years ago into everything you can see tonight when you look up at the sky. That structure, the cosmic web, the filaments and nodes and voids that give the universe its large-scale shape, could not have formed without dark matter, not in the time available, not in the way that we observe it. That is where we are going next. The night is quiet, the room is still, the universe outside is doing exactly what it has always done, expanding, cooling, moving through time at its own pace, indifferent to whether anyone is watching or not. And somewhere in the dark, particles are passing through you, right now, as they always have. You don't need to chase them, they are already here. We left Vera Rubin's rotation curves behind us, galaxies spinning too fast, dark matter halos inferred, the first cracks in the assumption that what we see is all there is. But rotation curves are a local measurement. They tell us about individual galaxies. They tell us about the mass distribution within a few 100,000 light years of a galactic center. They don't tell us about the universe as a whole. They don't tell us about the large-scale structure, the arrangement of matter across billions of light years, the way galaxy clusters are distributed, the way some regions of space are dense with galaxies and others are almost completely empty. To understand that, we have to zoom out enormously. Imagine pulling back from the Milky Way, first to the local group, the small cluster of about 50 galaxies, of which the Milky Way and Andromeda are the two largest members, occupying a region roughly 10 million light-years across. Then further to the Virgo supercluster, a larger structure of which the local group is a small peripheral member, spanning roughly 110 million light-years. Then further still to the Laniakea supercluster, the enormous structure of which the Virgo supercluster is itself just a part, containing approximately 100,000 galaxies and spanning 520 million light-years. And at this scale, the scale of superclusters and beyond, the universe reveals a pattern that no one anticipated before they had the data to see it. The universe is not uniform. It is not a smooth, evenly distributed collection of galaxies filling space in all directions. It is structured. It is web-like. It has long, thin filaments of matter connecting dense nodes of galaxy clusters, and between those filaments, vast empty regions called voids, where galaxies are almost entirely absent. This structure is called the cosmic web. It is real. It has been mapped. The Sloan Digital Sky Survey, which has cataloged the positions of hundreds of millions of galaxies across a significant portion of the observable universe, shows it clearly. The filaments and sheets and nodes and voids, a three-dimensional architecture of matter that spans the cosmos from one horizon to the other. And dark matter is the skeleton of that architecture. Not dark energy, not ordinary matter, dark matter. Here is why. In the very early universe, the first few 100,000 years after the Big Bang, the cosmos was a hot, dense plasma of ordinary matter and radiation. At those temperatures and densities, electrons and protons could not combine to form neutral atoms. The entire universe was ionized, and radiation and matter were tightly coupled. They moved together, scattered off each other, formed a single fluid. In this environment, ordinary matter could not gravitationally collapse. Any region that became slightly denser than its surroundings and began to attract more matter toward it would immediately be disrupted by the pressure of the radiation it was coupled to. The photons pushed back against the gravitational pull, preventing the kind of runaway collapse that forms structures. Dark matter, by contrast, does not interact with radiation at all. It is not coupled to the photon fluid. It is not disrupted by radiation pressure. So in the early universe, while ordinary matter was being held smooth and uniform by radiation pressure, dark matter was already beginning to clump, very slowly, in the first fractions of a second, and then the first seconds, and then the first minutes, and the first years, and the first millions of years. Dark matter was following its own gravitational instabilities, creating regions of slightly higher density, building up the first scaffolding of the cosmic structure. When the universe cooled enough, about 380,000 years after the Big Bang, for electrons and protons to combine into neutral hydrogen, ordinary matter was freed from the radiation. It was suddenly able to fall into the gravitational wells that dark matter had already begun to create, like water flowing into valleys that already existed, ordinary matter cascaded into the density concentrations that dark matter had been building for hundreds of thousands of years. Stars formed in those concentrations, galaxies formed, galaxy clusters formed, and the filamentary pattern of the cosmic web, the web of dark matter scaffolding filled in with luminous ordinary matter, emerged. Without dark matter to create those early density concentrations, the universe would not have had enough time to develop the structure we observe. The calculations are clear on this point. Simulations of a universe containing only ordinary matter, with no dark matter, produce a universe that is far smoother, far less structured than what we actually see. The galaxies that exist in those simulations are not arranged in the filamentary web we observe. They do not produce the pattern that surveys like the Sloan Digital Sky Survey reveal. With dark matter, with the right amount of dark matter, approximately 27% of the total energy density of the universe, the simulations reproduce the observed large-scale structure with remarkable accuracy. The cosmic web emerges, the filaments appear, the voids open up. This is called the lambda CDM model. Lambda for the cosmological constant, which represents dark energy, and CDM for cold dark matter. It is the standard model of cosmology. It is the framework within which modern astronomy operates, and its success in reproducing the large-scale structure of the universe is one of the strongest pieces of evidence that dark matter is real. Cold dark matter. That word cold is important here. It means that dark matter particles, whatever they are, were moving slowly relative to the speed of light at the time they decoupled from the rest of the universe's energy. Hot dark matter, particles moving at relativistic speeds in the early universe, would have streamed out of any density concentrations before structure could form, washing out the pattern before it could take hold. The fact that we observe the large-scale structure we observe, with small structures forming first and merging into larger ones, a process called hierarchical structure formation, is consistent with cold dark matter and inconsistent with hot dark matter. This is a constraint on the nature of dark matter. Whatever it is, it must have been moving slowly in the early universe. Neutrinos, particles that do exist, that do have a tiny but non-zero mass, that are produced in enormous quantities by stars and nuclear reactions, are candidates that have been considered and largely ruled out as the primary component of dark matter. They were produced relativistically in the early universe. They are hot dark matter, and hot dark matter does not produce the structure we observe. So it is not neutrinos, or at least not primarily neutrinos. Then what is it? You are sitting inside a question that has no verified answer. Not in 1980, not in 2000, not today. The question is the same. What is dark matter made of? The candidates are real. The experiments searching for them are real. The underground laboratories and the orbital telescopes and the particle accelerators are all real, all operating, all generating data, but the answer has not yet arrived. Let us go through the candidates. Let us understand what physics predicts and what experiments are trying to do. The leading candidate for most of the last 40 years has been the WIMP, the weakly interacting massive particle. WIMPs are a class of hypothetical particles predicted by theories that extend the standard model of particle physics, the framework that describes the known fundamental particles and forces, which has been extraordinarily successful in predicting and explaining phenomena from the behavior of electrons to the properties of the Higgs boson. The standard model has known incompleteness. It does not include gravity. It does not explain why there is more matter than antimatter in the universe. It does not explain the mass hierarchy of particles, why the top quark is so much heavier than the electron, for example. And it predicts that certain quantities that should, naively, be enormous are instead extremely small, a problem known as the hierarchy problem. Various theoretical frameworks that address these issues, particularly supersymmetry, which proposes that every known particle has a heavier supersymmetric partner, naturally produce candidate particles with exactly the properties needed for cold dark matter. They would be massive, in the range of 10 to 1,000 times the mass of a proton. They would interact via the weak nuclear force, one of the 4 fundamental forces responsible for radioactive decay, but extremely short-ranged and much weaker than electromagnetism or the strong nuclear force. They would not interact electromagnetically, meaning they would not absorb or emit light. They would not interact via the strong nuclear force. They would interact only gravitationally and via the weak force. This combination of properties means they would be produced in the hot, dense, early universe in the right abundance to account for the observed amount of dark matter. It means they would have been moving slowly enough to be cold dark matter, and it means that they would, very occasionally, interact with ordinary matter through the weak force, meaning that in principle they could be detected. This is the WIMP miracle, the fact that particles predicted independently by particle physics theory to solve problems that have nothing to do with dark matter turn out to have precisely the properties needed to explain dark matter. That coincidence, if it is a coincidence, has motivated decades of experimental effort. How do you detect a WIMP? If a WIMP passes through ordinary matter, there is a tiny probability that it will collide with an atomic nucleus via the weak force, not electromagnetically, not in a way that produces light or charges particles, but mechanically, it will impart a small amount of kinetic energy to the nucleus, causing it to recoil slightly from its normal position. This nuclear recoil is tiny, extraordinarily tiny. The amount of energy transferred is of order of a few kilielectron volts, comparable to the energy of an X-ray photon, but deposited in a single nucleus of a large atom. The signal is so small and so rare, perhaps only a handful of events per year per kilogram of detector material, at best, that detecting it requires going to extraordinary lengths to suppress every other source of signal. The primary background is cosmic rays, high-energy particles from space that rain down on the Earth's surface constantly, producing showers of secondary particles that would swamp any WIMP signal. To escape this background, dark matter detectors go underground, deep underground. The overburden of rock above the detector absorbs cosmic ray showers before they can reach the instrument. The deepest and most sensitive dark matter detectors in the world are located in underground laboratories. The LOX Zeppelin experiment, currently the most sensitive WIMP detector in the world, is located in the Sanford Underground Research Facility in Lead, South Dakota, a former gold mine now repurposed for physics, with the detector at a depth of approximately 1.5 kilometers underground. That 1.5 kilometers of rock reduces the cosmic ray flux by a factor of more than 1,000,000. The detector itself is a tank containing 10 tons of liquid xenon, cooled to -96 degrees Celsius and maintained at extreme purity. Liquid xenon is dense. Xenon atoms have large nuclei, making them good targets for WIMP collisions, and it scintillates when struck by particles, producing flashes of light and small ionization signals that can be detected by arrays of photomultiplier tubes surrounding the tank. When a particle interacts in the xenon, Lex Zeppelin produces two signals: a prompt flash of light from the initial interaction and a delayed pulse of light from electrons that have been liberated by ionization and drifted upward in an electric field. The ratio of these two signals tells the detector whether the interaction was with an electron, consistent with gamma ray or beta particle backgrounds, or with a nucleus, consistent with a WIMP interaction. The detector has been running, the data has been analyzed, and as of the most recent published results, no WIMP signal has been detected. This is not a failure exactly. Each null result constrains the properties WIMPs can have. With each experiment, the allowed space of WIMP masses and interaction cross-sections shrinks. The regions of parameter space that were once plausible have been ruled out one by one. Lex Zeppelin has pushed sensitivity to levels that would have seemed impossibly ambitious 20 years ago, and still no signal. The absence of a detection does not mean WIMPs don't exist. It means that if they exist, they are either lighter or heavier or interact more weakly than the simplest theoretical predictions suggested. The WIMP parameter space is not exhausted, but it is significantly constrained. And so, in parallel, experimenters are pursuing other candidates. The axion is a dark matter candidate that emerged from a different corner of physics, not from supersymmetry, but from an attempt to solve a separate puzzle in the strong nuclear force. The strong force, which binds quarks into protons and neutrons, has a symmetry called CP symmetry that it should in theory violate, but observations show that the strong force conserves CP symmetry to extraordinary precision. Why? This is the strong CP problem. One elegant solution, proposed in the 1970s by Roberto Pache and Helen Quinn, predicts the existence of a new particle called the axion, named by Frank Wilczek, who would share the Nobel Prize in Physics in 2004 for his contributions to our understanding of the strong force. Axions are predicted to be extremely light, much lighter than WIMPs, and to interact extraordinarily weakly with ordinary matter, but they would have been produced in large quantities in the early universe, and if they are stable, they would still be present today in vast numbers filling the universe. The search for axions is technically very different from the search for WIMPs. Axions can, in principle, convert into photons in the presence of a strong magnetic field, a process called the Primakov effect. Experiments like ADMX, the Axion Dark Matter Experiment, located at the University of Washington, use powerful superconducting magnets and microwave cavities tuned to specific frequencies to search for the signal of axion to photon conversion. These experiments are also running, also producing data, also so far not detecting a definitive signal, though they have been steadily narrowing the allowed axion mass range and are now probing the most theoretically motivated region of parameter space. You are listening to the silence of these detectors, a mile underground in the dark and the cold, waiting for a signal that may or may not come. The instruments are some of the most sensitive ever built. The people who built them have spent careers on this search. And the universe has, so far, not answered. This is what the frontier of science looks like. Not breakthrough after breakthrough, mostly patient waiting, with occasional incremental constraint. The history of physics is full of moments where the answer didn't come when it was expected, where the right idea was circling just outside the reach of the instruments, waiting for the technology to catch up. We may be in such a moment now. Or dark matter may not be particles at all. There are theorists who think the problem is not with the dark matter, It's with the theory of gravity. Mordechai Milgram in 1983 proposed a modification to Newton's laws of gravity at low accelerations, a framework called MOND, modified Newtonian dynamics, which can reproduce the observed rotation curves of galaxies without any dark matter at all. MOND postulates that below a certain critical acceleration threshold, roughly 1.2 times 10 to the minus 10 meters per second squared, gravity behaves differently than Newton's law predicts. MOND works remarkably well for individual galaxy rotation curves. Remarkably well, given only a galaxy's distribution of ordinary matter, MOND predicts the rotation curve with an accuracy that is, in many cases, better than dark matter models with multiple free parameters. But MOND fails at larger scales. It cannot reproduce the observed large-scale structure of the universe without introducing auxiliary hypotheses that themselves amount to something like dark matter. It struggles with the bullet cluster, a system we will examine in detail shortly, which provides one of the most direct pieces of evidence for dark matter, and it does not fit naturally into the framework of general relativity, though relativistic extensions of MOND exist. The scientific community has not abandoned the dark matter hypothesis in favor of MOND, but MOND remains an active area of research, and its successes at galactic scales are a genuine puzzle that dark matter models have to work harder to explain. The night is deepening, the questions are real, the uncertainty is real, the experiments underground and in orbit and at particle accelerators are real. The scientists running them have devoted years or decades of their lives to this search. And the dark matter, whatever it is real too, or at least its gravitational effects are real, so thoroughly documented now across so many independent lines of evidence that no serious cosmologist doubts that something is there. What it is remains the question. The universe does not owe us an easy answer, but it does leave clues, and the next clue, one of the most compelling, most direct pieces of evidence ever assembled for dark matter, comes from a collision of two galaxy clusters caught in the aftermath, frozen in a configuration that is almost impossible to explain any other way. That is where we are going next. But for now, the room is quiet. The air around you is filled with something you cannot feel. The particles move through you, if they are particles, and leave no trace. You are here, the universe is here, and the answer is somewhere in the space between what we can see and what we cannot. Rest in that space. Let it hold you. The night is long, and there is more to discover. Two galaxy clusters moving toward each other at 2,000 kilometers per second. Not a gradual drift, a collision, the kind of event that reshapes hundreds of millions of light years of space in a single catastrophic pass. And when it was over, when the gas had been stripped and slowed, and the galaxies had passed through each other, and the dust had, in astronomical terms, begun to settle, what remained was a configuration that almost no other explanation could account for. The mass was not where the gas was. The mass was somewhere else. The mass had kept moving through the collision as if the collision had never happened. That is where we are going tonight, to a place called the Bullet Cluster, 3.8 billion light years from Earth, a collision caught in its aftermath, a natural experiment that the universe performed without being asked, one of the most direct pieces of evidence ever assembled for the existence of dark matter. But before we arrive there, the full picture of the large-scale universe needs to come into focus, because the bullet cluster is not just a collision, it is a window into the way matter, visible and invisible, behaves at the very largest scales. And to understand what makes it so compelling, you first need to understand what the universe looks like from the outside. From a distance of hundreds of millions of light years, from the scale at which individual galaxies become single points of light in a structure so vast it is difficult to hold in the mind all at once. The cosmic web. That is where we begin. You're far from any single galaxy now. You are at a distance from which the Milky Way is not individually visible. It is simply one of hundreds of millions of faint points, distributed across space in a pattern that is not random, not uniform, but structured, organized, web-like. The cosmic web is the large-scale structure of the observable universe. It is composed of three distinct components: filaments, nodes, and voids. Filaments are the long, thin strands of matter, both ordinary and dark, that stretch across hundreds of millions of light years, connecting denser regions to one another. They are not uniform tubes, they are braided, irregular, denser at their cores, and more diffuse at their edges. Inside the filaments, galaxies cluster along their lengths, arranged like beads on a string, oriented along the direction of the filament's axis. The filaments themselves are the pathways along which matter flowed in the early universe, drawn by gravity toward the regions of highest density. Nodes are the intersection points where multiple filaments meet. They are the densest regions in the observable universe, the places where matter has had the longest time to accumulate, where enormous galaxy clusters containing hundreds or thousands of individual galaxies are concentrated into volumes that are, by cosmic standards, compact. The Coma cluster, where Fritz Zwicky first noticed the mass discrepancy in 1933, sits at such a node. The Virgo cluster, the nearest major galaxy cluster to our own local group, sits at another. These nodes are the brightest features of the cosmic web, glowing intensely in X-rays from the hot gas trapped within them, and in optical light from the billions of stars they contain. Voids are the spaces between the filaments and nodes. They are not empty. They contain a small number of galaxies and a diffuse distribution of matter, both ordinary and dark, but they are vast and nearly empty compared to the structures surrounding them. A typical void spans tens of millions to hundreds of millions of light years. Their interiors are quieter, regions where the flow of matter outward toward the filaments has left behind a kind of cosmic silence. The Buddha's void is one of the largest known. It spans approximately 330 million light years. It was discovered in 1981 by Robert Kirshner and colleagues at the Harvard-Smithsonian Center for Astrophysics, who were surveying galaxy positions in that region of the sky and found, unexpectedly, an enormous region almost entirely devoid of galaxies. Instead of the expected distribution, they found almost nothing, a hole in the map of the universe roughly spherical in shape and enormous in extent. They initially thought there must be an error. There was no error. If the Milky Way were located at the center of the Buddha's void, the nearest large galaxy would be approximately 150 million light years away. The night sky from inside the void would contain your own galaxy's stars, the band of the Milky Way crossing overhead, but looking outward in any direction, you would see almost nothing for a very long time. No nearby galaxy clusters, no filaments close at hand, a universe that would appear from the inside to be nothing more than a sparse scattering of faint points in an otherwise featureless dark. The evidence for the filamentary structure, the nodes, the web, all of it would require instruments of extraordinary sensitivity and surveys of vast areas of sky to detect, because the nearest evidence of large-scale structure would be so far away that the pattern would only emerge from the statistics of millions of measured galaxy positions, not from any single observation. You hold that image for a moment, the emptiness of the void from the inside, your galaxy's own stars arching overhead, and beyond them, almost nothing. Then you pull back. You return to the vantage point from which the full web is visible, and from here it is unmistakable. The cosmic web stretches in every direction, a three-dimensional architecture of matter spanning billions of light years, intricate and coherent and real. And dark matter is the skeleton of that architecture. Here is how it formed. The universe began approximately 13.8 billion years ago in a state of extraordinary density and temperature. In the first fractions of a second, the fundamental particles were in a state of continuous creation and annihilation. As the universe expanded and cooled, particles began to persist. In the first 3 minutes, protons and neutrons combined to form the nuclei of the lightest elements: hydrogen, helium, trace amounts of deuterium and lithium. This process is called Big Bang nucleosynthesis, and the abundances of these light elements, measured today in the oldest and most pristine astronomical environments, match the predictions of standard cosmology with remarkable precision. For the next 380,000 years, the universe remained a hot, dense plasma. Electrons had too much thermal energy to be captured by nuclei. The universe was filled with a coupled fluid of ordinary matter and radiation, tightly bound together. In this state, the density fluctuations seeded by quantum processes in the earliest moments of the universe could not grow freely. Whenever a region became slightly overdense and began to collapse under gravity, the radiation pressure built up and pushed back, causing the region to expand again. This produced oscillations, sound waves in the cosmic plasma, that prevented the runaway growth of structure in ordinary matter during this period. Dark matter, present from the earliest times in the same proportions as today, behaved differently. It does not couple to radiation, it does not feel radiation pressure, and so it was free to begin clumping, slowly but steadily from the earliest cosmic times. The tiny density perturbations in the dark matter distribution could grow under their own gravity without being disrupted by any opposing force. Over hundreds of thousands of years, while ordinary matter oscillated and the radiation held it smooth, dark matter was quietly building density concentrations, not dramatic ones. The universe was young and the density contrasts were still very small, but real ones. Gravitational wells, deepening slowly, spreading through the early universe, becoming the first faint outlines of what would eventually be the cosmic web. Then, 380,000 years after the Big Bang, recombination occurred. The universe had cooled enough to approximately 3,000 Kelvin for electrons to combine with protons and form neutral hydrogen atoms. With no more free electrons to scatter from, the photons decoupled from the matter and streamed freely through space. They became the cosmic microwave background. Ordinary matter, suddenly freed from the radiation field, was free to fall. And it fell into the dark matter wells, like water flowing into depressions that already exist in a landscape. Ordinary matter cascaded toward the concentrations of dark matter that had been accumulating for hundreds of thousands of years. The dark matter's gravitational head start was the critical ingredient. Without it, The small density perturbations in ordinary matter alone would have taken far longer to grow into the structures we observe. The universe would be smoother, galaxies would be rarer, the great clusters at the nodes of the cosmic web would be absent or dramatically less massive. With dark matter providing the initial scaffolding, the first stars began to ignite within the first few 100 million years after the Big Bang. The first galaxies formed within the first billion years. Over the following billions of years, galaxies merged and grew along the dark matter filaments. Galaxy groups formed, galaxy clusters accumulated at the nodes. The cosmic web we observe today emerged from the dark matter structure that had been building since before any stars existed. The Millennium simulation, completed in 2005 by the Virgo Consortium, using supercomputers at computing centers in Germany and the United Kingdom, made this process visible in a way that no observation could. Using the computational equivalent of 10 billion dark matter particles in a simulated cubic volume 2 billion light-years on a side, beginning with initial conditions derived from CMB measurements, the simulation evolved the dark matter distribution forward for 13.7 billion years of cosmic time. The result, when compared to real galaxy surveys, was striking. The large-scale structure of the simulated universe, the distribution of dark matter halos, the arrangement of filaments, the sizes and depths of the voids, matched the observed large-scale structure of the real universe with remarkable fidelity. The Sloan Digital Sky Survey, which had painstakingly measured the three-dimensional positions of hundreds of millions of real galaxies, showed patterns nearly identical to the patterns in the simulation. This agreement was not guaranteed. It was a prediction, made using only the known laws of gravity, the observed initial conditions from the CMB, and the cold dark matter hypothesis, and the prediction was confirmed by observation. Without dark matter in the simulation, the web fails to form. The structures are too small, too smooth, too weakly clustered. The universe looks wrong. The match between simulation and observation, present when dark matter is included and absent when it is removed, is one of the most powerful arguments for the reality of dark matter as a physical constituent of the cosmos. Dark matter is not a patch on a broken theory. It is a required ingredient in a framework that, with it included, reproduces the universe as we observe it, from the smallest galaxies to the largest superclusters. Now, the bullet cluster. The formal designation is 1E 0657558, a pair of galaxy clusters 3.8 billion light-years distant in the southern constellation Carina that have undergone a high-velocity collision. The two clusters, one significantly larger than the other, moved toward each other, met and passed through. The smaller cluster, having punched through the larger one like a projectile, is now moving away on the other side. The collision happened approximately 150 million years ago. What we observe today is the aftermath, a natural experiment frozen in time, available for any telescope powerful enough to read what it says. Each galaxy cluster has three major components: the galaxies themselves, individual stellar systems containing billions of stars, separated from one another by millions of light-years within the cluster volume, the intra-cluster medium, an extremely hot, diffused plasma of hydrogen and helium ions at temperatures between 10 million and 100 million Kelvin that fills the space between galaxies, and in a typical cluster contains more ordinary baryonic mass than all the galaxies combined, and the dark matter halo, the dominant mass component, the invisible gravitational scaffold that provides the majority of the cluster's total mass. In the collision of two such clusters, these three components behave in ways dictated by their physics. The galaxies, numerous as they are separated by such enormous distances relative to their sizes that the collision between two clusters is not a collision between stars. It is a collision between structures. The probability of any two individual stars from the two clusters actually impacting is negligible. The galaxies pass through each other as two widely spaced swarms of points, deflected somewhat by gravity, but otherwise continuing in roughly their original directions. After the collision, they are distributed in two groups, one for each cluster, now moving apart on the other side of the event. The intracluster gas is different. The plasma is a charged electromagnetic fluid. When the gas of one cluster meets the gas of the other, the two interact. The charged particles of one plasma feel the electromagnetic field of the other. Ram pressure builds up, the resistance of one medium moving through another at high velocity. The collision shocks the gas. It compresses it into a bright wedge of superheated plasma at the leading edge of the smaller cluster. It slows it dramatically relative to the galaxies. The gas of both clusters piles up between the galaxy populations. The Chandra X Ray Observatory, an orbiting telescope launched by NASA in 1999, designed to focus X-rays that would otherwise be absorbed by Earth's atmosphere, observed this X-ray emission in the bullet cluster system in spectacular detail. The images show the compressed, shock-heated gas as a bright, bullet-shaped region of X-ray emission, denser at the leading edge where the smaller cluster's gas is pressing through the larger cluster's gas, with a characteristic bow shock at the nose, trailing off behind. The shape is unmistakable. It is where the gas has been decelerated and compressed by the collision. Now, where is the mass? If the clusters were composed entirely of ordinary matter, the answer would be straightforward. The intracluster gas contains the majority of the ordinary mass, so the center of gravity of each cluster should follow the gas. The gas slowed, the gas piled up between the two galaxy populations, so the gravitational center should be there, concentrated in the region of brightest X-ray emission between the galaxies. To measure the actual mass distribution, the team led by Douglas Clough used weak gravitational lensing, the statistical analysis of the shapes of background galaxies seen through and around the cluster system. Images from the Hubble Space Telescope and multiple ground-based observatories were used to catalog the positions and apparent shapes of hundreds of thousands of faint background galaxies. The gravitational field of the cluster system distorts these shapes, slightly stretching them tangentially relative to the direction toward mass concentrations. By measuring the pattern of this shear across the entire field, it is possible to reconstruct a map of the total projected mass distribution without any assumption about what that mass is made of. The mass map shows two distinct concentrations, one centered on each galaxy population. Not on the gas, on the galaxies. The brightest X-ray region, where the gas has accumulated between the clusters, is not where the mass is. The mass is offset by several 100,000 light-years from the gas. The gas and the mass have been separated by the collision. This separation is the signature of dark matter, the dominant mass component of each cluster, the component that accounts for most of the total gravitational mass, did not interact with the gas of the other cluster. It passed through without experiencing any drag. It kept moving with the galaxies. Because it is similarly collisionless, it does not interact electromagnetically. In a universe with no dark matter, The ordinary baryonic gas is the primary mass component of a galaxy cluster. The mass follows the gas. In the bullet cluster, the mass does not follow the gas. The mass is spatially separated from the gas, centered instead on the collisionless galaxy populations. The offset between the X-ray gas peak and the lensing mass peak in the smaller cluster is approximately 200 kiloparsecs, roughly 650,000 light-years. This is not a marginal statistical result. It is clearly visible in the composite images. The blue contoured lensing mass, the pink-orange X-ray emission, offset, distinct, separated. The paper was published in the astrophysical journal Letters in August 2006. Its title was Direct, a direct empirical proof of the existence of dark matter. That choice of language, direct empirical proof, reflects the strength of the observational case. Scientists rarely use the word proof. The bullet cluster earned it. Subsequently, similar analyses were performed on other merging cluster systems. MAX J0025, 4 POWS 1222, known informally as the baby bullet, shows the same pattern. Several other merging clusters have now been analyzed with similar results. The bullet cluster is the clearest and most dramatic case, but it is not unique. It is part of a pattern that the universe has produced multiple times, in different places, at different scales, all telling the same story. You are watching the bullet cluster from outside now. The X-ray glow between the clusters, the two galaxy populations to either side, the invisible mass traveling with the galaxies, having ghosted through the collision without friction, without slowing, without any sign of its presence except the way it curves the light of distant galaxies behind it. It passes through, it does not interact, it does not stop, and yet it is the dominant mass component of the universe, the thing that holds galaxies together, the thing that built the cosmic web, the thing that made the universe habitable for stars and planets and everything on them. Something that has never been directly detected, that leaves no track in any detector, that interacts with light only through gravity, by bending it, by deflecting it, by creating the lensing distortions that allow us to map what we cannot see. Now we move to a different kind of evidence, not from collisions, not from rotation curves, not from gravitational lensing alone, from the oldest light in the universe, a signal that carries information from a time 380,000 years after the Big Bang, and that encodes within its fluctuation pattern the most precise measurements of the dark matter density ever made. The cosmic microwave background. The CMB is the thermal radiation released at the epoch of recombination, the moment when the universe cooled enough for neutral atoms to form and the photon matter plasma to decouple. Those photons, the light of the early universe, the last thing the plasma emitted before it became transparent, have been traveling through space ever since, for 13.4 billion years, cooling as the universe expanded, stretching from optical and infrared wavelengths into the microwave range. Until today, they form a faint, nearly uniform glow, coming from every direction at a temperature of exactly 2.725 Kelvin, 2 degrees and 725 thousandths of a degree above absolute zero. This background was first detected in 1965 by Arno Penzias and Robert Wilson at Bell Laboratories in New Jersey. They were not looking for it. They were calibrating a horn antenna designed for satellite communication, and they kept finding an unexplained noise signal, equal in intensity from every direction, consistent across all seasons, present regardless of where the antenna pointed. After ruling out every terrestrial source they could think of, including a pair of pigeons nesting in the antenna horn, they concluded the signal was real and cosmological. They received the Nobel Prize in Physics in 1978. The CMB is not perfectly uniform. It has temperature fluctuations at the level of 1 part in 100,000, tiny variations from point to point across the sky, tracing the density fluctuations in the early universe at the moment of recombination. These fluctuations are not random. They are the imprint of the baryon acoustic oscillations, the sound waves in the primordial plasma, frozen into the light at the instant the universe became transparent. The Planck satellite, a European Space Agency mission that operated from 2009 to 2013 and released its final data products in 2018, produced the most precise map of the CMB temperature fluctuations ever made. Its measurements of the CMB power spectrum, the statistical description of the amount of variation at each angular scale, are precise to fractions of a percent across an enormous range of scales. In that power spectrum, dark matter has left specific fingerprints. In the primordial plasma, before recombination, density perturbations oscillated as sound waves. Ordinary matter and radiation compressed together, then expanded together, in a cycle driven by the competing forces of gravity and radiation pressure. Each oscillation mode, each scale of perturbation, oscillated at a frequency determined by the sound speed of the plasma and the physical size of the perturbation. The state of each mode at the moment of recombination determined its contribution to the CMB temperature fluctuation pattern. Modes at maximum compression produced hot spots. Modes at maximum rarefaction produced cold spots. Dark matter participated in the gravitational part of this process, providing additional gravitational attraction that deepened the potential wells into which the baryon photon fluid was falling, but it did not participate in the radiation pressure. It does not couple to photons. It does not contribute to the pressure term in the oscillation equations. Its effect on the acoustic oscillations is therefore distinctive and measurable. It enhances the amplitude of odd-numbered acoustic peaks relative to even-numbered ones. The deeper the gravitational wells provided by dark matter, the stronger the compression on the downswing. The compression associated with the first, third, and fifth acoustic peaks, relative to the expansion on the upswing, the second, fourth, and sixth peaks. The ratio of the first acoustic peak to the second acoustic peak in the CMB power spectrum is a direct measure of the ratio of dark matter to ordinary matter in the early universe. Planck measured this ratio with extraordinary precision. The result: dark matter constitutes approximately 26.8% of the total energy density of the universe, with an uncertainty of less than 1%. 27% from the oldest light, from a time before galaxies, before stars, before planets, before anything that now exists in the visible universe. The same number that galaxy rotation curves suggest, the same number that gravitational lensing of clusters produces, the same number that the bullet cluster analysis is consistent with, the same number that the Millennium simulation requires to reproduce the observed large-scale structure. 27% from every direction, every method, every instrument, every era of observation. The CMB also tells us what dark matter is not. By measuring the baryon density separately from the dark matter density, each leaves a different imprint on the acoustic peak pattern. Planck determined that ordinary baryonic matter makes up approximately 4.9% of the total energy density. This is consistent with the abundances of light elements produced during Big Bang nucleosynthesis. The dark matter is not baryonic. It is not cold gas. It is not failed stars. It is not black holes in sufficient numbers. It is not any form of ordinary matter that has simply been overlooked. It is something else, something non-baryonic, non-luminous, gravitationally significant, present from the earliest times, distributed throughout the universe at the same density ratio as always. Something that was there when the first photons were released. Something that shaped the acoustic oscillations in the primordial plasma. Something that left its fingerprint in the oldest light in the universe. Something that, 13.4 billion years later, is still here, moving through you, through the walls of the room you are in, through the planet beneath you. You don't feel it. You can't. It does not interact with the atoms of which you are made, except through gravity, and the gravitational force of individual dark matter particles is so vanishingly small that no biological system could ever sense it. But it is here, right now, as it has always been. The night is deepening now. The air is still. The facts that have been moving through this story, the rotation curves, the cosmic web, the bullet cluster, the CMB peak ratios, the underground detectors listening in the dark, begin to settle into something quieter, not resolved, not concluded, but present, stable, real. The search for dark matter is one of the most consequential scientific investigations of this era. More than 40 years of targeted effort, multiple generations of experiments, each more sensitive than the last. The Lux Zeppelin detector in South Dakota, listening at 1.5 kilometers depth. The Xenond detector in the Gran Sasso laboratory beneath the Apennine Mountains of Italy at 1.4 kilometers depth. The Panda X4T experiment at the Jinping Underground Laboratory in Sichuan Province, China, one of the deepest underground physics facilities in the world, at more than 2.4 kilometers below the surface. Each of these detectors uses liquid xenon, a dense, scintillating medium whose large atomic nuclei make it a favorable target for WIMP interactions. Each is surrounded by multiple layers of shielding, water tanks, lead, copper, carefully purified materials chosen for their low intrinsic radioactivity, all designed to suppress the background signals that would otherwise swamp any faint WIMP-induced nuclear recoil. Each is running, collecting data, publishing results, and so far, no signal. Not yet. The null results are not failures, they are constraints. Each experiment that does not find a WIMP tells us something precise about what WIMPs cannot be, how heavy they can't be, how strongly they can't interact. With each generation of experiment, the allowed parameter space shrinks. The theoretical models that were once well motivated become increasingly constrained. The WIMP hypothesis is not dead, but it is under pressure. The simplest, most natural versions of supersymmetric WIMPs, the ones that theorists would have predicted most confidently in the 1980s, have largely been ruled out by the combination of LHC collider searches, direct detection experiments, and indirect detection with Fermi. The surviving WIMP models require more fine-tuning, more specific parameter choices. Meanwhile, the Axion remains a compelling candidate, and the experiments searching for it, ADMX, HiStack, CAP, Abracadabra, are entering the most theoretically motivated regions of Axion mass and coupling space. If the Axion is the dark matter, the next decade may see the first hints of a signal in one of these experiments. Or the answer may be something no one has yet thought of. The history of physics is full of this. The neutrino was proposed theoretically to save conservation of energy in beta decay 20 years before it was detected. The Higgs boson was predicted in 1964 and confirmed in 2012. The gravitational wave was predicted by Einstein in 1916 and first detected in 2015. The universe is reliably more interesting than the theories that describe it, and the gap between prediction and detection can be long. The work continues, patient, methodical, not romantic, just real. You are settling now. The rhythm of the words is slowing. The facts are still here. The rotation curves, the bullet cluster, the CMB, the detectors in the dark beneath the mountains, but they no longer require you to follow them closely. They are simply present, background, real, part of the universe you live inside, whether you attend to them or not. The dark matter is where it has always been, in the halo of the Milky Way, in the filaments of the cosmic web, in the space around you and through you and beneath the floor. It does not need you to understand it to keep doing what it does. And you do not need to understand it to be here now, at rest, breathing slowly, held by gravity to a small planet orbiting an ordinary star in a galaxy embedded in an invisible structure that has been here since before the first light. The night is yours. Let the universe do the rest. Sleep comes when it comes, and when it does, the dark matter will still be moving through you, exactly as it has every night of your life, without announcement, without trace, without end. That is not nothing. That is the universe doing what it does. The experiments beneath the mountains are not the only searches underway. The Fermi Gamma Ray Space Telescope, launched by NASA in June 2008, and still operational, orbits Earth at an altitude of approximately 550 kilometers in a low polar orbit that allows it to scan the entire gamma-ray sky once every 3 hours. It is designed to detect gamma-ray photons, the most energetic form of electromagnetic radiation produced by the most violent processes in the known universe. Among the signals Fermi is designed to look for is the gamma-ray signature of dark matter annihilation. If dark matter is made of WIMPs that are their own antiparticle, which is a prediction of some supersymmetric models, then when two WIMPs encounter each other, they can annihilate. The annihilation produces standard model particles, quarks, leptons, gauge bosons, depending on the WIMP model. Those particles then decay and produce, among other things, gamma-ray photons. The energy of those photons would be characteristic of the WIMP mass, and the spatial distribution of the signal would follow the dark matter density distribution, concentrated toward the galactic center, where the dark matter halo is densest. The galactic center is the brightest region of the gamma-ray sky. It is also extraordinarily complex, populated by pulsars, supernova remnants, molecular clouds, a central black hole with a mass of approximately 4 million solar masses, and numerous other processes that produce gamma-ray emission. Disentangling a potential dark matter annihilation signal from all of these astrophysical backgrounds is one of the most difficult data analysis challenges in modern astrophysics. Fermi has been observing the galactic center continuously for more than 15 years. An excess of gamma-ray emission above what known astrophysical sources can account for has been measured by multiple analysis groups, a diffuse signal roughly spherically symmetric around the galactic center, with an energy spectrum consistent in shape with what WIMP annihilation would produce for a WIMP with a mass of roughly 40 to 50 gigaelectron volts, about 40 to 50 times the mass of a proton. This excess is real. It is not a statistical fluctuation. Multiple independent groups, using different analysis methods and different source models, have confirmed its presence. What is debated is its origin. One interpretation, it is WIMP dark matter annihilation. The signal properties, spatial distribution, energy spectrum intensity, are consistent with what is predicted for a particular class of WIMP models. Another interpretation, it is a population of millisecond pulsars, old, rapidly rotating neutron stars that emit gamma rays, too numerous and individually too dim to be resolved by Fermi as distinct point sources, but collectively contributing a diffuse background that mimics a smooth, spherically symmetric excess. Millisecond pulsars are known gamma ray emitters. The galactic bulge region is expected to contain a large population of them. Whether that population is large enough and bright enough to account for the observed excess is a question that depends on models of pulsar formation and evolution that themselves have uncertainties. The debate has not been resolved. Some subsequent analyses have found statistical evidence in the data for the point source nature of the excess, consistent with the pulsar interpretation. Other analyses have found the excess to be smoother than a population of unresolved point sources would predict, more consistent with the dark matter interpretation. The systematic uncertainties in both directions are large enough that neither interpretation has been definitively confirmed or ruled out. This is again what the frontier looks like: a real signal, a real debate, real uncertainties on both sides. The answer waiting for more data, more sensitive instruments, more refined theoretical models. The Cherenkov Telescope Array, a next-generation ground-based gamma-ray observatory currently under construction at sites in La Palma in the Canary Islands and at the Paranal Observatory in Chile, will have significantly better angular resolution and sensitivity than Fermi in the high-energy gamma-ray band. When it reaches full operation, it will be able to probe the galactic center with enough spatial resolution to help distinguish the dark matter and pulsar interpretations of the excess. That is a few years away. The work continues. From underground detectors to space telescopes to particle colliders, the search for dark matter is the broadest coordinated scientific effort currently targeting a single unknown: the Large Hadron Collider at CERN, the most powerful particle accelerator ever built. Located in a circular tunnel 27 kilometers in circumference beneath the French-Swiss border near Geneva, collides protons at center of mass energies of up to 13 tera electron volts, probing the physics of the electroweak scale and beyond. If dark matter particles can be produced in proton-proton collisions at LHC energies, they will escape the detectors invisibly, carrying momentum that does not register in the calorimeters or tracking detectors, but their escape will be inferred from momentum imbalance. In any collision, the total transverse momentum of the initial state is zero. The protons arrive head-on. The total transverse momentum of the collision products must therefore also sum to zero. If dark matter particles are produced and escape, the visible products will have a net transverse momentum that does not add to zero. There will be missing transverse energy, pointing in the direction the dark matter particles went. Searches for events with large missing transverse energy, produced in association with a hard jet, a photon, or a Z or W boson, have been conducted at the LHC by both the ATLAS and CMS experiments, using the full dataset from Run 1, Run 2, and now Run 3. No clear signal of dark matter production has been found. Again, not a failure, a constraint. For WIMPs interacting through mediator particles with specific properties, the LHC has set limits on the mediator mass and coupling strength that complement and extend the limits from direct detection. The combination of LHC direct detection and indirect detection limits together constrain WIMP models from multiple directions simultaneously, a triangulation that makes it increasingly difficult for simple WIMP models to hide. The simplest WIMP models have been significantly constrained. They have not been ruled out entirely, but the parameter space is smaller than it was. The search continues at higher luminosities, with upgraded detectors, with more sophisticated analysis techniques. And in parallel, the theoretical community is exploring alternatives. Sterile neutrinos, hypothetical heavy relatives of the known neutrinos, are a dark matter candidate that would fit into the standard model with a minimal extension. They would have been produced in the early universe through mixing with ordinary neutrinos, and if their mass is in the kilo-electron-volt range, they would be warm dark matter, not quite cold, not quite hot, but intermediate. Warm dark matter models make different predictions for the small-scale structure of the universe compared to cold dark matter, predicting fewer small satellite galaxies around the Milky Way and a less cuspy dark matter distribution in galactic centers. The observed number of small satellite galaxies around the Milky Way has at various times been cited as either a problem for cold dark matter models, the missing satellites problem, or a confirmation of warm dark matter. More recent work, accounting for the effects of baryonic physics, star formation, supernova feedback, and the reionization of hydrogen in the early universe on the small-scale structure of galaxies, has largely reconciled the satellite galaxy numbers with cold dark matter predictions. But the debate about the details continues, and sterile neutrinos remain a live candidate. There are also more exotic possibilities. Primordial black holes. Black holes formed in the early universe from density fluctuations before any stars existed were briefly reinvigorated as a dark matter candidate following the first detection of gravitational waves from merging black holes in 2015, when it was noted that the black hole masses involved were heavier than typically expected from stellar evolution. If a significant fraction of dark matter were primordial black holes in the mass range of tens of solar masses, the gravitational wave signal from their mergers might be detectable by LIGO and Virgo. Subsequent analysis of the gravitational wave event rate and the mass distribution of detected mergers has constrained but not eliminated this possibility. Primordial black holes can make up at most a few percent of the dark matter in some mass ranges, and are ruled out as the dominant component across most of the mass spectrum by a combination of gravitational microlensing surveys, CMB distortions, and gravitational wave statistics. But the window is not entirely closed. The range of possibilities is vast. The experiments are numerous. The theoretical landscape is rich with candidates and models and alternatives, and the answer, the true identity of the thing that makes up 27% of the universe, is still waiting somewhere in that landscape to be found. You are listening to the patience of that search now, not the drama of it. There is less drama in science than the popular image suggests. More repetition, more data collection, more analysis, more null results carefully documented and published, more constraints added to the growing map of what dark matter cannot be, which is a different kind of progress from finding what it is, but still progress. The scientists running these experiments are not working in a state of excitement. They are working in a state of concentration, long shifts monitoring detector status, long hours analyzing data, looking for anomalies, long months waiting for enough data to say something meaningful, long years between the design of an experiment and its first meaningful results. This is what scientific discovery actually looks like from the inside, not the moment of breakthrough, which does sometimes come and which is genuinely extraordinary when it does, but the long, careful, patient accumulation of information that makes the breakthrough possible when it arrives. You are breathing more slowly now. The sentences have been finding their own rhythm for a while, a rhythm that doesn't ask you to follow closely, that allows the words to pass through and leave their residue without demanding full attention. That is what this kind of story is for. Not to be studied, not to be memorized, to be present in, the way you are present in a room, aware of the walls and the air and the quiet, without needing to describe any of it. The dark matter is in the room with you. It has always been, in the walls, in the floor, in the air around you, in you, streaming through without interacting, carrying its mystery politely and without announcement. Billions of particles per second per square centimeter. If they are particles, passing through, not stopping, not speaking. The universe keeps its secrets at a pace humans find frustrating. We have been looking in earnest for less than a century. The universe has been here for 13.8 billion years. The dark matter has been here for all of that, from the first fractions of a second, from before the first nuclei formed, from before the first photon traveled freely through transparent space. We are by comparison new. And new things learn slowly at first, then faster, then sometimes in a rush that surprises everyone. The detectors are running, the sky is being watched, the accelerators are colliding, the theorists are writing, the data is accumulating. The answer is out there. Whether it comes tonight or in 10 years or in 50, it will come to people doing exactly what the scientists in South Dakota and Italy and China and Geneva are doing right now, showing up, collecting data, staying careful, staying curious, not giving up on the question just because the answer hasn't arrived yet. That is enough to know that the search is real, that the work is real, that somewhere in the dark beneath the mountains, instruments are listening with more patience than any human could sustain alone, and that those instruments are the extended patience of everyone who built them and maintains them and believes the universe is answerable. Let that carry you now. The room is dark, the air is still. The universe outside is doing exactly what it has always done. And the dark matter is here, moving through you, patient and ancient and entirely unaware of being searched for. Rest in that. Let the searching continue without you for a while. The night has more story left, but that story can wait until the next part of the dark settles in. For now, breathe, let go. The universe is large enough to hold the question and the questioner both. And it has been doing exactly that, without effort, since before the first stars burned. There is a galaxy called NGC 1052 DF2. It is approximately 65 million light-years from Earth. It is a large, diffuse galaxy, unusually faint for its size. Its stars spread thin across a volume that should, by every expectation, be filled with far more than what is visible. By the standards of a typical galaxy of comparable mass, it should have a dark matter halo several times more massive than its visible stars. It doesn't. In 2018, a team led by Peter Van Dokkum at Yale University published measurements of the velocities of 10 globular clusters orbiting NGC 1052 DF2. Globular clusters are dense, ancient balls of stars, some of the oldest objects in galaxies, and their orbital velocities around the galaxy's center are a tracer of the total mass enclosed within their orbits, exactly as stellar velocities in a disk galaxy trace the rotation curve. The globular cluster velocities in NGC 1052 DF2 were low, very low, consistent with a total mass that is, within measurement uncertainty, equal to the mass of the visible stars alone. There is little to no room for a dark matter halo in the budget. A galaxy with almost no dark matter. The reaction to this discovery was immediate. Some saw it as a challenge to the dark matter hypothesis. If dark matter is a required ingredient for galaxy formation, how does a galaxy exist without it? Others saw it differently. Others saw it as confirmation. Here is the logic. If dark matter did not exist as a real physical substance, if the apparent dark matter effect were simply a modification of the law of gravity, as Mondi proposes, then every galaxy should show the same modification. The gravitational law applies everywhere. You cannot have some galaxies with dark matter effects and others without them if what you're calling dark matter is actually just gravity behaving differently at low accelerations. But if dark matter is a real substance, if it is a physical component that can be present in greater or lesser amounts depending on a galaxy's formation history, then galaxies with very little dark matter are not just possible, they are expected. Not common, but possible. Galaxies can, under the right circumstances, lose their dark matter halos through tidal stripping, the gravitational influence of a much more massive nearby galaxy, pulling the dark matter away, or simply form in environments where the initial dark matter concentration was unusually low. NGC 1052 DF2 exists in the vicinity of NGC 1052, a massive elliptical galaxy. The tidal interaction between the two may have stripped DF2 of much of its dark matter halo over billions of years of orbital interaction. In Mund, this kind of stripping does not apply to dark matter because there is no dark matter to strip. A galaxy without dark matter is, paradoxically, stronger evidence for dark matter than a galaxy with it, because it shows that dark matter is a substance, present in some places, absent in others, subject to the same physical processes that move other kinds of matter around. Not a law, a thing. Several other dark matter deficient galaxies have since been identified in the same region of space, reinforcing the picture. The universe, it turns out, contains galaxies that are dark matter rich and galaxies that are dark matter poor, just as it contains galaxies that are gas rich and gas poor, old and young, massive and dwarf. Dark matter distributes itself according to history and environment. It is not a fixed property of the gravitational law. It is a component. That is where the story of dark matter stands at the present moment, not resolved, not complete, but clear in its outlines. Something non-baryonic, non-luminous, present in varying amounts in and around galaxies, building the cosmic web, shaping the CMB, passing through ordinary matter without interacting. 27% of the total energy budget of the universe, the dominant form of matter by a factor of 5. And alongside it, the other unknown, the deeper unknown in some ways, the 68%. Dark energy. You have heard that number before in passing, the cosmological constant, the thing that is accelerating the expansion of the universe. The reason the universe is not just expanding, but expanding faster with each passing moment, so that the most distant galaxies are receding from us at speeds that will, in the far future, carry them beyond any possible contact. Dark energy is not dark matter. It is a different phenomenon entirely, but understanding the full picture of the universe requires placing dark matter within the larger context of the energy budget, the inventory of what the cosmos is actually made of. The discovery that the universe's expansion is accelerating came in 1998 from two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams were using Type 1a supernovae as standard candles, objects of known intrinsic brightness whose apparent brightness in the sky allows their distance to be calculated. By measuring the distances and recession velocities of supernovae at high redshift, meaning very far away, meaning very long ago, they could determine how the rate of expansion of the universe had changed over cosmic time. The expectation was that the expansion should be slowing down. Gravity acts on all the matter in the universe, and gravity is attractive. The mutual gravitational attraction of all the matter should be decelerating the expansion that the Big Bang set in motion. The question was, how much deceleration? Enough to eventually halt the expansion and cause the universe to recollapse, or just enough to slow it without stopping? What both teams found instead was that the expansion is not decelerating at all, it is accelerating. The distant supernovae were fainter than expected, meaning they were farther away than a decelerating universe would have placed them. The universe is expanding faster now than it was billions of years ago. Some form of energy is driving this acceleration. It has a negative pressure, it pushes outward rather than pulling inward, and it appears to be uniformly distributed throughout space, not concentrated in any structure. It has been named dark energy. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for the discovery. The simplest description of dark energy is the cosmological constant, a term that Einstein himself introduced into the equations of general relativity in 1917 as a way of producing a static universe before Hubble's 1929 observations of galaxy recession showed the universe was expanding. Einstein later called the cosmological constant his greatest blunder. It turned out to be necessary after all, not to keep the universe static, but to describe its accelerating expansion. The cosmological constant represents a fixed energy density of empty space, a property of the vacuum itself. It does not dilute as the universe expands. It does not cluster. It simply is uniformly everywhere at a constant energy density, driving the expansion of space at an accelerating rate. Why does it have the value it has? Why not zero? Or why not some much larger value? This is the cosmological constant problem, and it is one of the deepest unsolved problems in theoretical physics. Quantum field theory predicts that the vacuum should have an enormous energy density from the zero-point energies of quantum fields. The observed value of the cosmological constant is smaller than that prediction by a factor of approximately 10 to the power of 120. That is the largest discrepancy between theory and observation in all of physics. The resolution to this discrepancy is not known. So the universe is 73% unknown in its energy budget, 27% dark matter, unknown in its identity, 68% dark energy, unknown in its fundamental nature, 5% ordinary matter, known, mapped, understood in its physics, the subject of centuries of scientific investigation. 5%? You let that settle. Everything you have ever seen, every star in every sky, every galaxy in every telescope image, every atom in every planet, every breath you have ever taken, 5% of the total. The universe is not mostly made of what you can see. It is mostly made of things that science has not yet explained. Not gaps in the data, real physical components, established by multiple independent lines of evidence, whose properties are measured and whose effects are observed, but whose fundamental nature remains open. This is not a failure of science. It is a description of where science stands at a particular moment in a very long process. 200 years ago, the composition of the sun was unknown. 100 years ago, the existence of other galaxies was not established. 60 years ago, the CMB had not been detected. 25 years ago, the accelerating expansion had not been discovered. The picture keeps getting stranger, more complete in some ways, stranger in others. The universe keeps turning out to be more surprising than the theories that describe it. That is the honest situation. Now let the night deepen. The scientific accounting is done for tonight. The inventory has been taken. 5% ordinary matter, 27% dark matter, 68% dark energy. The evidence has been laid out. The searches have been described. The candidates have been named. The null results have been counted. What remains is simply the scale of it. You are on a planet orbiting a star. That star is one of approximately 200 to 400 billion stars in the Milky Way galaxy. The Milky Way is one of approximately 2 trillion galaxies in the observable universe, the region of space from which light has had time to reach us since the Big Bang. Each of those galaxies is embedded in a dark matter halo. Each is connected to others by filaments of dark matter and gas. Each sits within the larger structure of the cosmic web, which extends to the observable horizon in every direction. The observable universe spans approximately 93 billion light-years in diameter. That is the region we can, in principle, observe, bounded not by the edge of the universe, which may be infinite or may be finite, but is in either case larger than what we can see, but by the finite speed of light and the finite age of the cosmos. Within that volume, dark matter constitutes approximately 27% of the total energy density. The total mass of dark matter in the observable universe is estimated at roughly 6 times the total mass of ordinary matter, approximately 10 to the power of 53 kilograms of dark matter, compared to roughly 2 times 10 to the power of 52 kilograms of ordinary matter. These are numbers without human scale. They are not meant to be held precisely. They are meant to convey a proportion. The darkness outweighs the light by a factor of 6. And the darkness is not passive. It is not simply there. It built the structures that allowed the light to exist. Without dark matter, there are no galaxy clusters. Without galaxy clusters, there are no large galaxies. Without large galaxies, there are no generations of stars massive enough to fuse the heavy elements. Without heavy elements, there are no rocky planets. Without rocky planets, there is no you. The dark matter that passes through you is not incidental to your existence. It is a prerequisite for it. You are made of 5% matter that condensed out of processes that dark matter made possible. The oxygen in your lungs was forged in stellar cores that formed in dark matter halos that assembled before the first stars ignited. The carbon in your cells was scattered by supernovae that happened inside galaxies whose shapes were determined by the dark matter scaffolding they formed within. You are, in a very real physical sense, a consequence of dark matter, not a direct consequence. Dark matter did not make you, but the chain of causation that leads from the Big Bang to you passes through dark matter unavoidably at multiple steps. This is not a metaphor. It is a description of the causal structure of the universe as we currently understand it. The night is very quiet now. The words are finding a slower tempo. Each sentence has a little more space around it than the one before. You have traveled a long way tonight, from Fritz Zwicky in 1933, staring at numbers that didn't add up in the coma cluster, through Vera Rubin's flat rotation curves, through the cosmic web and its formation history, through the bullet cluster in the CMB and the underground detectors and the gamma-ray sky and the accelerating expansion and the dark matter deficient galaxy and the full inventory of the cosmos. It is a long story. It spans almost a century of observation and 100 years of scientific argument and the light travel time of the entire observable universe. And at the center of it, not the center geographically, but the center of the open question, is something that has not been named, something that outweighs everything glowing in the cosmos by a factor of 5, something that the best instruments ever built, listening in the deepest quiet ever achieved, have not yet heard. But they are still listening. That matters. The listening matters. Not because the answer is guaranteed to come, or because the timeline is known, but because the history of science shows that persistent, careful, well-designed experiments eventually encounter what they are looking for, sometimes in expected ways, more often in unexpected ones. The neutrino was predicted in 1930 by Wolfgang Pauli, who proposed it reluctantly, calling it a desperate remedy because he was sure something with no charge and almost no mass could never be detected. It was detected in 1956 by Clyde Cowan and Frederick Rains, using a nuclear reactor as a source and a large tank of cadmium chloride solution as a detector. 26 years from prediction to detection, the technology had to catch up with the question. The Higgs boson was predicted in 1964. It was detected in 2012 at the Large Hadron Collider using a detector the size of a small city built by thousands of physicists over more than 2 decades, 48 years from prediction to detection. The accelerator had to be built. Gravitational waves were predicted by Einstein in 1916 as a consequence of general relativity. They were first directly detected in September 2015 by the LIGO interferometers, using instruments capable of measuring a displacement 1/10,000th the width of a proton across a 4-kilometer baseline. 99 years from prediction to detection, the sensitivity had to be achieved. Dark matter was first suspected in 1933. Its gravitational effects are now among the most thoroughly documented phenomena in modern astrophysics. Its fundamental identity remains unknown. We are 92 years in. There is no guarantee, but there is precedent for patience. The room is very still. The breath is slow. The thinking that this story requires has been dissolving gradually for some time now, replaced by something quieter. Not sleep yet, but the state just before it, where the body has made its decision and the mind is catching up. Let it catch up. The dark matter is here. The universe is here. The instruments are running. The questions are real. And you have been here for all of it tonight. A brief luminous arrangement of 5% matter that spent a few hours of the night tracing the outline of the 95% it lives inside. That is enough. That is more than enough. This is quiet science at bedtime. If you have made it this far, through the galaxy clusters and the underground detectors, and the oldest light in the universe, a subscribe and a like mean everything, and the notification bell means you will be here the next time there is a story worth telling in the dark. There will be more stories. The universe has not run out of them. The future of the universe is worth holding for a moment, not as a comfort or a warning, but simply as a fact, because the dark matter story does not end with the present day. It continues forward into a future governed by the same physics that has governed everything so far, playing out on timescales that dwarf everything we have discussed tonight. The universe is currently 13.8 billion years old. It is in what cosmologists call the Stelliferous era, the age of stars. Stars are forming, burning, dying, scattering their elements. Galaxies are evolving. The cosmic web is slowly changing as matter continues to fall along filaments toward the nodes. This era will continue for approximately another 100 trillion years, 10,000 times longer than the current age of the universe, before the last low-mass stars finally burn out. During this entire time, dark matter halos will persist. They are stable. They are not burning fuel. They are not evolving in the way stars do. The dark matter halo of the Milky Way will still be here when the last red dwarf in the galaxy has exhausted its hydrogen and faded to a cold cinder. The dark matter does not age in the way ordinary matter does. But on even longer timescales, the accelerating expansion driven by dark energy will begin to assert itself more dramatically. The expansion of the universe is currently slow enough that gravity still holds galaxies and galaxy clusters together. The Milky Way and Andromeda are gravitationally bound. They will merge in approximately 4.5 billion years into a single larger elliptical galaxy. The local group, the roughly 60 galaxies in our immediate vicinity, will eventually merge into a single giant galaxy over tens of billions of years. But beyond the local group, the accelerating expansion is already pulling galaxies away from us faster than they can approach. The most distant galaxies we can currently observe are already receding at apparent speeds greater than the speed of light, not because anything is moving through space faster than light, but because the space between us and them is expanding, and enough space expanding slowly still adds up to a fast recession at large distances. Over trillions of years, the accelerating expansion will continue to carry galaxies beyond our observable horizon. One by one, the distant galaxies will redshift to invisibility, their light stretched to such long wavelengths that no instrument could detect them. In the very far future, on timescales of trillions of years, the observable universe for any civilization that might exist within the Milky Way's eventual merged remnant will contain only the stars of that local structure, embedded in darkness, with no external galaxies visible at all. The cosmic web will not be observable. The evidence for the Big Bang, the CMB, will have redshifted to wavelengths so long that detecting it would require an antenna the size of a solar system. The universe will appear, to any hypothetical future observer, static and isolated, a single island of stars in an infinite dark. The evidence for dark matter, the rotation curves, the gravitational lensing signatures, the CMB acoustic peaks will still be present in principle. The dark matter halos will still be there. But the cosmic context that makes the evidence interpretable, the comparison of our galaxy to other galaxies, the observation of merging clusters like the Bullet cluster, the large-scale structure surveys that reveal the cosmic web, will have been erased by the expansion. future civilizations, if any exist, which is a question physics cannot answer, will face an epistemological situation opposite to ours. We have the CMB as a window into the past. We have billions of galaxies to compare. We have the full breadth of the cosmic web to measure. We know we are one galaxy among 2 trillion in an observable universe 13.8 billion years old. They will not have that. The expansion will have hidden it. In a certain sense, we are living in the ideal epoch for cosmology, early enough that the universe has not yet isolated itself into separate, unreachable islands, late enough that the first generations of stars have seeded the universe with the elements needed for chemistry and planets and biology. The window for observing the full breadth of the cosmos is open now. It will not always be. This is not a cause for urgency. The window will remain open for billions of years, but it is a reminder of what a particular moment in the universe's history this is. We are living in an era with enough information to piece together the history of the cosmos from beginning to present, with the CMB as our early universe document and the galaxy surveys as our large-scale structure map. We have the bullet cluster, we have the rotation curves, we have the acoustic peaks. We have, in other words, the evidence. What we are still working on is the explanation. The explanation will come, maybe in a form we expect, maybe in a form that will require revising the question. Science has repeatedly discovered that the universe is stranger than the framework used to describe it. General relativity was stranger than Newtonian gravity. Quantum mechanics was stranger than classical physics. The accelerating expansion was stranger than any static or decelerating model. Dark matter may be strange in ways we have not yet imagined. It may be multiple things, not one. It may interact in ways that have not been accounted for. It may have internal structure, a dark sector, with its own forces and its own particles, interacting with ordinary matter only through gravity, a parallel physics playing out invisibly alongside everything we know. Or it may be something much simpler than any of that, a single particle with a single mass produced in the right abundance by the thermal history of the early universe, waiting in the data of the next generation of detector, waiting for the instrument that hasn't been built yet. The dark matter does not care about the elegance of its explanation. It is what it is. It has been what it is since the universe was less than a second old. It will continue to be what it is long after every star currently burning has faded. The patience of the universe exceeds anything human timekeeping can accommodate. And you are here, briefly, within it. A few decades of consciousness, a few hours of listening tonight. The entire span of a human life is less than the blink of a cosmic eye, a phrase so often used it has lost its force, but which is mathematically true in a way worth sitting with quietly at least once before sleep. 13.8 billion years, your life. The ratio. And in that ratio, you had time to ask the question, time to build the telescopes and the detectors and the particle accelerators, time to measure the rotation curves and the lensing maps and the acoustic peaks, time to go underground beneath a mountain in South Dakota and wait in extraordinary quiet for a signal from something that makes up 27% of the universe. That is what the 5% does. It asks questions about the 95. No other fraction of the universe, as far as we know, does anything like that. The night is fully here now. The words are softer. The breathing is slow. Whatever thinking this story called for has done its work and is settling. You don't need to carry any of this with you. The dark matter will carry itself. It has been doing that for 13.8 billion years without assistance. You are allowed to simply be here, in the dark, held by gravity to a small warm planet, aware of the quiet. The universe is out there. The instruments are running. The search continues. And you are here. That is enough. Everything you heard tonight is real. Dark matter is out there right now.